Welcome back. In this video, we're going to go into a little bit more depth into distortion energy theory for static failure. And the reason I want to do this is because we'll be using distortion energy throughout when we talk about fatigue failure, because it ends up being a very good way to average the stress from different types of forces. So we might have different amounts of fatigue wear from different types of loads, and so how do you put those all together? Well, the answer is going to be by using this distortion energy approach. But in order for us to understand that, we need to dive into a little bit of depth of distortion energy. So distortion energy theory predicts that a part will fail when the energy related to the shape change is the same as the energy that causes of shape change of an element to fail. So what that looks like is we put some part under some, let's do a tensile load. This would just be one particular stress element, and that stress is going to cause some strain, and that strain is in two parts. We could call it the strain which makes the shape larger, so volume change, and it's also going to be in part deformation, which causes elongation. So remember, we're talking about ductile failure theory, so this is shape change. So distortion failure theory, distortion energy says when the energy associated with this shape change is equal to the shape change energy for failure, a part will break. So that's fundamentally what we're going to be doing, and I'm not going to delve too much into the to energy equation. Of course, you can follow along in the book to do that. Suffice it to say that the energy, the strain energy, is equal to 1/2, in general, the strain in one direction, so this would be 1, 2, and 3, we'll use principal directions, times the principal stress 1, plus the strain 2 and principal stress 2, the strain in 3 times the principal stress in 3. So that's how that works out. And that's generally the strain energy associated with that failure. So we're going to need to make one huge giant assumption. And this giant assumption is that the amount of strain in every direction is the same because the modulus of elasticity in every direction is the same. So what that means is that a material stretches as much in the x, y, or z direction, or any direction we want. Precisely, we mean that the material is isotropic, meaning that it has the same properties in every direction. Now, as I mentioned before, this is not true for many materials, but we're going to be looking a lot at steel and aluminum and some materials where that is the case. So, suffice it to say, we're going to have is the energy related to distortion in the shape-changing aspect looks something like this: 1 plus Poisson's ratio over 3 times this modulus of elasticity, if we believe it's all the same in every single direction, times the yield stress squared. And that's what's going to cause strain energy of failure. And of course, by failure here, we mean that we've reached the yield strength. So the amount of strain energy for it to break is the amount of strain energy at the yield strength, where breaking means it yields. So it's a little bit circular in that. So what that results in is us coming up with a generic stress state called von Mises stress, this average stress, that is a relation of the principal stresses. So we'll do the difference of the principal stresses squared. And all of that over 2. And then the square root, because we're looking for the square root comes from finding that squared stress value. Now, for many situations, on the outside surface of materials, we're worried about plane stress. And in plane stress, we have principal stresses in two directions, but not in the third. So sigma 3, well, one of the sigmas equals 0, not necessarily sigma 3. We'll use the ordering system where sigma 1, 2, and 3 are in order of maximum. So under that concept, we'll use sigma A and sigma B here. And then we can say that sigma A squared plus sigma B squared, which those are the two non-zero ones, minus sigma A times sigma B to the 1/2. Where those are values for principal stresses. Now we could come back in here, and we know how to find principal stresses, say from Moore's circle, for example. And we remember that equation, and it has square roots in it. And we can come back in here and solve for what those principal stresses are, and simply swap out our sigma A's, sigma B's, with the equations for how we get there. So how we get there is actually pretty straightforward. It ends up being von Mises stress is, we'll do x direction sigma x plus sigma y. This will obviously look exactly the same. Minus sigma x times sigma y, and then add 3 tau x y to correct for the fact that there is shear stress in a non-principal direction. So the principal stresses are squared, and the shear stress is squared, and the combination is not, and all of that is to the 1/2. So let's take a generic bar here, and we'll put it under some bending. We'll call that M1. And we can put it under some torque, T, and maybe we'll put it under some axial stress, A. But we could also have it bending moments in multiple directions, right? So maybe it bends into the page in this direction as well. So that looks a little bit messy, and we'd obviously have a hard time coming up with this, but we need to just figure out what the stresses in each direction do to each force in that direction. And from this, we can figure out, well, where is the maximum stress located? Where's the maximum stress element? And we could come up with a stress element at that location. And I'll throw some values in here just so we can do some computation. And we'd see some x direction tension of, say, sigma x due to bending would be about 20 kpsi. We could do the same thing in sigma y due to bending in that other direction, and let's call it 15 kpsi. But then we also have the axial portion, so we can add that if this is along the axis here is our x, then we could say that is also sigma x axial equals 5 kpsi. So in total, sigma x is going to be equal to 25 kpsi. And we could of course add stress in the same direction as long as it is in fact acting in the same direction. And then let's add from the torsion some positive shear stress on this element, tau x y, on the x face acting in the y direction, or vice versa, y face acting in the x direction, doesn't matter, they're the same, and call that 10 kpsi. So that's a stress element, and obviously that looks a little bit messy in that form, so I generally describe a stress state, which is a little bit easier to deal with as a matrix. So we've got 25 sigma x, we've got 15 sigma y, and sigma x, or tau xy, was 10. So we could run this through either our principal stress calculations in Moore's circle, we could find the eigenvalues, and if we did that, what we'd come up with is what our goal here is, what is the principal stress? So from eigenvalues, if you use a calculator, either the one on Blackboard or the one on your calculator, you'd come up with stress values of 31.18, 8.82, and 0, of course, since this is plane stress. So our nomenclature says that that's sigma 1, that's sigma 2, and that is sigma 3. Of course, you could also use the principal stress equations from Mohr circle. Sigma 1 and sigma 2 equals, would be 25 plus 15 over 2, plus and minus the square root. I'll try to write it small here. 25 minus 15 over 2 squared, the differences, or half the difference, plus tau xy, which is 10 squared. So what value should you get from this? Well, if you get anything different than the eigenvalues, then you've done something wrong with either one of the approaches, because they will be exactly the same thing. 31.18, 8.82, and 0. Obviously, it won't make a difference. Obviously, you didn't find a sigma 3 using this approach. So that's the one difference. So now that we have the principal stress values, we can actually apply the distortion energy failure theory and see whether we think our part will break. In order to do that, we need to know what our part's made out of. So let's choose aluminum, because it's generally a cheap metal to start with. And aluminum has a yield strength somewhere around 35 to 45, let's call it 40 kpsi as a good average. So will our part break if it's under this stress? Well, according to distortion energy, what we can do is we can say is the von Mises stress greater than that yield strength? Or for maximum shear stress theory, we can say is the maximum shear stress our part is under equal to the stress shear stress equivalent of that yield strength. So let's look at those two. So distortion energy has sigma prime equal to sigma A squared. This is just rewriting it from before, sigma B squared minus sigma A sigma B, where those are the principal non-zero stress values. Ignore that. So we would have, in our situation, we'd have 31.18 squared plus 8.82 squared minus the multiplication of those two, 31.18 times 8.82, and then take the square root of that. And that's our von Mises stress. So we come up with an equivalent average stress, another way to call von Mises stress, as 27.84 kpsi. So what if we wanted to do maximum shear stress theory? So this is distortion energy, and this is maximum shear stress theory. Well, maximum shear stress theory says, well, tau max is the largest difference. So sigma 1 minus sigma 3 over 2. So we'd have 31.18 minus 0 over 2, or the maximum shear stress is 15.59 kpsi. All right. So shear stress 15.59, von Mises stress says 27.84. So under distortion energy, we would say that the factor of safety against yielding is the yield strength over the stress that we're at, or in our case 40 kpsi divided by about 28 kpsi. Kpsi over kpsi. Factors of safety should always be do not have units. So that means our factor of safety against yielding, according to distortion energy, is 1.4. Now let's compare that to maximum shear stress, which would say that our factor of safety against yielding is the yield strength over 2 divided by the maximum shear stress. So half the yield strength, or the yield strength in shear, would be an equivalent way of saying that. So our yield strength under this formulation would be 40 kpsi divided by 2 times 15.59. So obviously 15 times 2 is going to be about 30. We end up with a yield factor of safety of 1.28. So if we compare these two, we'll notice that the distortion energy will always be greater than or equal to the yield strength. In this case, it's greater than. And that is the factor of safety. And the reason is that maximum shear stress theory is more conservative. But distortion energy actually lines up with our data better. So in this class, we'll mostly be using distortion energy. So why is this important? Well, let's go back for just a moment and look at distortion energy. We were able to come up with one value, the von Mises stress. This is a big deal. And relate it to stress from all sorts of different things. We had whatever stress is related to sigma x, whatever stresses and loadings caused sigma y, the difference between those two, and whatever causes shear stress. Could be torsion, could be direct shear, it doesn't matter. So that's the value of this equation, is that we could put in multiple types of loading. And we have one stress value at the end of this. And we can compare that stress value to things that we care about. Well, that'll about do it for this video. Until next time.